Hi everyone. Today we are hosting Oleg, who is going to give a talk about our recent paper.
Okay. So I will be talking about our joint work with Fabrizio Grandoni, Giuseppe Italiano, Nikos Parotsidis, and Przemysław Uznański. And this is actually the first time I'm talking about my own results, so I'm still pretty stressed and in a deep shock, but I hope it won't be a disaster today. The title is AllPair LCA in DAGs, breaking through the O of n to the 2.5 barrier. So we'll be talking about graph problems, and especially if we have a dense graph, it has O of n square edges. So basically the best time complexity for algorithms we will run on these graphs is of the same order of magnitude. So this is kind of our goal, to achieve this best possible time complexity. And for most classical problems and algorithms, they actually achieve this running time. However, there are some graph problems that seem to be much harder. In particular, there is a problem of computing all-pair shortest paths in weighted graph. And there is a simple algorithm that does that in n-cube time. However, there hasn't been any considerable progress in this problem. So we don't know any much better algorithms, and it's actually a popular conjecture that it cannot be done. Yeah. On the other hand, there are numerous examples of graph problems that can be solved using some kind of matrix multiplication routine. So these algorithms run in time n to omega, where omega is the exponent of the best known matrix multiplication. And we will also consider them fast, since omega is pretty close to 2. Yeah, so we all know that the naive multiplication of matrices run in n-cube. And there has been a very big line of research starting in 1969 with the Strassen algorithm. People were trying to actually improve on this complexity. And quite surprisingly, using very sophisticated tools, we can get pretty close to 2. It's 2.37 something. We will use these fast matrix multiplication algorithms today, but we will treat them as a black box. And actually, they, the current state-of-the-art algorithms, they are not really that practical, because the constants are huge galactic numbers. So there is no hope for using these particular algorithms in practice. However, it is very interesting from the theoretical point of view. And the pretty widely believed conjecture is that omega is actually 2, so that we believe that probably we can even multiply 2 matrices in n² time. Okay, so there is also pretty considerable class, pretty big class of graph and geometric problems that actually seems to fall in between these two complexities of n to omega and n cube. We will call them the intermediate complexity problems. And they are, at the very first glance, they don't really seem to be related with each other. However, the interesting thing is that for all of them, the running time of the best known algorithm that we have is n to omega plus 3 divided by 2, which is actually a geometric mean of n to omega and n cube. To be exact, actually, for some of these problems, we can get slightly better algorithms using the power of fast rectangular matrix multiplication. However, these improvements, they vanish if we assume that omega equals to 2, actually. There has been a recent line of research that tries to actually scrutinize the equivalences and relations between these intermediate complexity problems. And the example of examples of the recent work include one of the Przemysław papers from 2019. There is also a very recent work of Andrea Lincoln, Adam Polak, and Virginia Wasilewska-Williams from ITCS 2020. And there is a very recent paper that studies these equivalences even more from Fox 2020 by Wasilewska-Williams and Xiu. So the main point of our interest is a problem of computing LCAs in a directed acyclic graph. So probably I should explain what do I mean by LCA in a DAG, because it's non-obvious. Let us look at the example that I drew here. So for vertices U and V, we have multiple common ancestors. These are A, B, C, D, and F. However, I will call C and D the lowest common ancestors because they don't have any children that are also ancestors of U and V, right? So, for example, A is not a lowest common ancestor of U and V because B and D are children of A, and they are both also common ancestors of U and V. But for C and D, there are no such vertices, so they are LCAs. So you can see that actually an LCA, it's not need to be a single vertex. That's one thing, and also there might be no common ancestor at all. So therefore, no lowest common ancestor, obviously. For example, let's say for vertices E and C, there are no common ancestors at all. So in our problem, we want to compute some lowest common ancestor for every single pair of vertices. And you can see on this slide an example graph and a matrix with lowest common ancestors for every single pair. Notice that, again, as I actually mentioned before, it does not need to be, basically, it does not need to be symmetric. So you can see that for vertices 5 and 6, I wrote an LCA. They have two LCAs, 3 and 4, and I wrote one in the one direction and the other in the other. Is it clear for now? Are there any questions? Okay, I assume that it's clear. So there has been some research about this problem in the past. So it was actually stated in 2001 by Bender et al. And they provided a simple lower bound of n to omega. Basically, it is easy to see that computing AllPair LCAs is at least as hard as computing intransitive closure. And they also provided an n to omega plus 3 divided by 2 algorithm for this problem. And later on, Kowaluk and Lingas, and later Chumai, Kowaluk, and Lingas improved upon this original algorithm using a reduction to maximum witnesses problem, maximum witnesses of Boolean matrix multiplication. And the best known algorithm for this problem used maximum witnesses and rectangular matrix multiplication. And given the current bounds on omega, it ran in time n to 2.569. And the interesting quality of these algorithms was that, assuming the conjecture that omega actually equals to 2, they all run in time n to 2.5. So basically, up until now, this problem of computing AllPair LCAs was in the class of intermediate complexity problems. And our result is actually an improvement. The first time in 13 years, we improved upon the algorithm of Chumai, Lingas, and Kowaluk. And it runs in, given the current bounds on omega, it runs in O of n to 2.447. And it might not seem to be that much of an improvement, but what is probably the most important is that, assuming that omega equals to 2, we actually get a running time of n to 2 plus 1/3. So it's like a new complexity class, like a new complexity class of some intermediate complexity problems. And to this end, we actually don't use maximum witnesses, and it's pretty interesting. Yeah, that's a nice idea. So we don't use maximum witnesses. It's pretty interesting because up until now, many people sort of thought about these two problems together. But our techniques and our result, in some sense, might suggest that these problems are separated in some way. We also have a very recent result that is actually not included in the paper. And this is work with Przemek and Adam Polak, that any improvement to max-min product implies faster algorithm for the problem that we study. Okay, so now I will talk briefly about these previous approaches to the AllPair LCA problem. So the key ingredient was the usage of maximum witnesses for Boolean matrix multiplication. So what it is? So assume that we multiply two Boolean matrices, and we have some non-zero entry in the resulting matrix. So this non-zero entry can come from many different multiplications of 2 ones that we could get, right? And here on the slide, we can see we have highlighted in green the rightmost one that actually matches the other one in the second matrix, and we call this any one that actually is a witness that of non-nullity of the entry in the resulting matrix. We call it a witness, but the rightmost one we call a maximum witness. Actually, we can say that the index of this rightmost one is the maximum witness for the resulting entry in the resulting matrix. Is it clear? Because I think that I might have confused you here.
I have a question.
Yeah.
This is matrix multiplication or Boolean and you do an OR?
This is Boolean matrix multiplication. So the multiplication is we have and summation is OR.
But you are not forced to do any combinatorial tricks. This is instead of Boolean, think of it as 0-1 matrices, and you are free to use n to the omega.
Yeah, obviously, right? You can actually use the normal matrix multiplication, right? And in the resulting matrix, you just look if you got 0 or non-zero. If it's non-zero, there has been some matches, right? Yeah, this is actually a very important point.
Yeah, thanks.
Yeah, so this shows that we can compute a Boolean matrix product in n to omega using the standard matrix product. Okay. So now the algorithm of Chumai, Kowaluk, and Lingas basically run as follows. We pick some parameter x, and we divide the first matrix into n over n to x matrices, each of with n to the x. And we make a similar partition of the second matrix, but this time it's like it's rotated by 90 degrees. So we have vertical stripes on one side and the horizontal stripes on the other. And now we can compute n over n to x Boolean matrix products. And yeah, basically we take one horizontal stripe, like if it's like the first stripe, then we take the first one on the other side and we multiply them, and so on. And then we can observe that if you have a non-zero entry in the product of our two matrices, and if it has a witness in appropriate interval, then actually we need to have a non-zero entry in the appropriate product of two stripes. Okay. So actually, if we want to, if we have this, if we know that in the resulting matrix, the ijth entry is non-zero, and we want to compute a maximum witness for it, the only thing that we need to do is to actually find, like, first we need to find which is the rightmost vertical stripe that gives us like a non-zero entry in the multiplication with the corresponding horizontal stripe, right? And then we can brute force over this interval and just check one by one if we had a match. So how long does it take? We have n over n to x stripes. So this is n to 1 minus x. And each multiplication takes n to omega. So this is n to omega plus 1 minus x. Then possibly for every entry of the resulting matrix, so there are at most n square entries, we need to find the stripe. So this is there are n to 1 minus x stripes, so we get n to 3 minus x. And then we brute force inside the stripe. It takes n to x, and again, we might need to do that n squared times. So this gives us n to 2 plus x. Okay? Now we can see that actually we can drop n to 3 minus x because it's dominated by n to omega plus 1 minus x, and then we optimize. And after optimizing, we get n to the omega plus 3 divided by 2. So the complexity of intermediate complexity problems. And actually, the only other thing that Chumai, Kowaluk, and Lingas do is the usage of rectangular matrix multiplication, because it turns out that you can, for rectangular matrices, you can actually multiply them slightly faster than n to omega. Okay, is that clear? Like at least the idea. Okay, yeah. So that was their algorithm for maximum witnesses, and now what they did is was to actually, yeah, if you want to compute AllPair LCAs, you just fix a topological order of your graph. You compute a transitive closure, and then you transpose the adjacency matrix of it, and you compute maximum witnesses of the product with the not transposed adjacency matrix. And this is actually pretty easy to see that after that you get, for every pair of vertices, you get like this witness gives you a common ancestor with the highest possible index in topological order. So naturally, it needs to be an LCA, because it has the highest number in topological ordering. Yeah, and basically that was the algorithm. Yeah, so now I will talk about our solution. So we will use the power of rectangular matrix multiplication. It turns out that you can multiply it slightly faster than n to omega, and there are numerous bounds known. Yeah, the most important thing that we need to remember is the notation. We denote by omega 1 x1 the exponent of the fastest multiplication of n times n to x and n x times n matrices. Okay. There are also other matrix products, and we will use a max-min product where the addition is replaced by max and the multiplication is replaced by min. And turns out that it also can be multiplied in n to omega plus 3 divided by 2 times. And actually, we can always also use like a slight modification of algorithm of Duan and Petty to use their algorithm to also compute rectangular max-min product. And again, the ideas here were similar to what we have just seen, because basically the complexity comes from the fact that we balance two terms, one that comes from matrix multiplication and one from brute force computations. And we will also use witnesses for Boolean matrix multiplication. And the important thing is that actually, if we don't care if our witness is maximum, and we only care about extracting any witness, this can be done in a time very similar to the normal matrix multiplication, which was shown by Alan et al. In the 90s. Yeah. So the notion of chains and anti-chains in DAG will be instrumental to our algorithm. So a chain is just a path. But till the end of this talk, I will assume that actually our graph is transitively closed, because we can compute a transitive closure in n2 omega, and because it doesn't change answers. Basically, if LCAs in a DAG and in its transitive closure are the same. And also, I will assume that vertices of the graph are labeled by numbers, and these numbers form some sort of some arbitrary topological order. Okay. Yeah. So we have a chain, and let's say we have some vertex u and its ancestor inside the chain. Okay. So actually, you can see that like the whole prefix of this chain, these are all of these vertices, they are ancestors of u, right? So if you have another vertex, this is a similar situation. So actually, the common prefix of these two, these are the common ancestors that are inside the chain that we are considering. So if we know for every vertex u, we know the number of the last ancestor inside this chain, basically we can pretty easily for two vertices u and v compute all of the common ancestors that are inside this chain, and in particular the ancestor that has the highest number in the topological ordering. So this gives us, like the intuition is that this gives us some kind of a candidate for our LCA for u and v. Yeah. So what happens if we could partition our graph into few chains? Let's say we have n to x chains that partition like the whole graph. So well, then basically we can easily, for every vertex, compute like this number of the last ancestor inside the chain. For example, for vertex u, these are colored in red, right? And then if we have another vertex v and we want to compute LCA of u and v, we need to take minimum of, like for every chain we need to take a minimum of 2 numbers, and we need to take a lot of these minima, and what we do, we take a maximum among these minima. Okay, because then we know that this is actually like the best candidate. Yeah. And so this is probably not that surprising. We can use a max-min product to speed up our computation. So what we do is we form a new matrix, and one dimension is like vertices, and the other is chains. And for every vertex and for every chain, we write this index of the last ancestor of the vertex inside this chain. And then when we compute this rectangular max-min product, it gives us the best candidate for LCA among all of these chains. And by algorithm of Alon et al., it takes n to omega 1 x1 plus 2 plus x over 2 time. Okay, so the other important structural insight is what happens if we have an anti-chain. So observe that, yeah. So observe that if we have an anti-chain, and we have some, let's say, candidates for LCA inside this chain, this anti-chain, yeah, like on the slide, then actually it doesn't matter for us which one we take, because there is no path from one to the other. So yeah, they don't clash. So let's say that we could actually partition graph into a few anti-chains. So actually we can also sort them according to the topological order. And then for every anti-chain, we could compute, like, extract any candidate, and then take the candidate from the last anti-chain in the topological order. Yeah. So since we don't care about which candidate we take, we can use witnesses for Boolean matrix multiplication. So how we do it? For every anti-chain, we again form a matrix. For every vertex and every anti-chain, we write one if there is excuse me for a second, we write one.
You write one when, I mean, you take one particular single anti-chain, and you write one if there is an ancestry relation.
Yeah, that's why I get so confused. Yeah, these are not anti-chains. This is one anti-chain. Oh yeah, sorry, sorry for this. The second dimension is the vertices of the anti-chain. Yeah, and now we take one if there is an edge from this vertex from anti-chain to the vertex in our graph. Okay, yeah, and we do that for every single anti-chain. So it takes n to 1 minus x plus omega 1 x1 in total. So these insights motivate the notion of A-B decomposition that we use in our algorithms. So A-B decomposition is just the composition of DAG into at most A chains and B anti-chains. So the algorithm really is, we compute a transitive closure, we compute some n to x, n to 1 minus x decomposition, and I will show in a second how to do that. Then we solve problems separately for chains and anti-chains. for chains and for every pair, we get some candidate for LCA that comes from chains, and similarly for anti-chains. And at the end, we just take a maximum from these two candidates, and it turns out that if we take a good topological ordering, it just works. So basically, these techniques were pretty much known before. However, the key ingredient is how to compute this decomposition efficiently. So there is a naive approach that we just, if you want to compute a k n over k decomposition, we can just extract k chains longest chains iteratively, and it's easy to see that the remaining part can't be covered by n over k anti-chains. However, this is too slow. In our case, it would work in n to 2 plus x time. And if we look at the complexities, we need to balance 3 different parts, one that comes from chains, one from anti-chains, and one from the decomposition. And actually, if you're trying to optimize on X, it gives exactly the same complexity as in Chumayko-Waluk and Lingas. So what we need is a faster decomposition. So what we do? So this algorithm is pretty similar to the classical standard algorithm for computing longest increasing subsequence in a sequence of numbers. So the idea is that we maintain the layers, and basically the ith layer consists of vertices for which the longest chain that ends at this particular vertex is of length I. Okay? And then it's very easy to see that these layers form anti-chains, because you just cannot have an edge between 2 vertices. Okay. So we just process our vertices one by one according to our topological ordering, and we build this structure of layers, and when we process the next vertex, we just try to find the layer that it fits into. So what we do, we just find the rightmost layer for this vertex where he had an ancestor, and then we just add it to the next one. Okay. So the very important thing, and it will turn out in a second why is it so important, is that whenever some layer grows such that it has k vertices, we just remove it. And we start from scratch. We run the same algorithm on the reduced number of vertices. And we add this anti-chain to our AB decomposition, to our n to 1 nx n to 1 minus x decomposition. Okay? Actually, here I should say k n over k, sorry. Yeah. Again, if actually we find a chain that is at least of length n over k, so we have many layers, we just find this chain and we remove it, we extract this, and we run our algorithm again on the reduced number of vertices. So if we were to perform all of these operations naively, it would again take the same time as a naive algorithm. However, the main trick is that we can actually perform this searching for the appropriate layer for the new vertex, we can do this faster using binary search. Why is it? So observe that if we have a path of vertices, and we have like the last vertex here in green, the last vertex of this path, then because the graph is transitively closed, it has edges to all of the previous vertices in this path. So when we try to fit a new vertex into our structure of layers, we can just binary search in the number of the layer. Yeah, and basically that's it. Because we extract the long layers, one query of the inside the binary search takes at most O of k, right? So the complexity of one binary search is then k log n. So for every round of our algorithm that ends with either removing a chain or anti-chain, we make one binary search for every vertex at most, so it's nk log n. There are at most k plus n over k rounds because we cannot extract more. So in our application, this gives us n to 1 plus 2x plus n square time. And now if we look at the graph of complexities, this actually gives us an improvement over the previous algorithms. And yeah, and this combined with the best currently known bounds on omega 1x1, this gives us the claimed n to 2.447 algorithm. Inside the paper, we actually show even faster decomposition that runs in n squared time. And actually, this implies that any improvement to max-min product allows us to compute this chain part faster. And this actually yields improvement to AllPair's LCA problem. So there are also, still there are numerous open problems left. So one thing, and it's like a common theme of many such problems and algorithms, is that we don't really know how to leverage the sparsity of the graph. Mainly the problem is that after maybe we can have a sparse graph at the input, but after we compute this transitive closure, it might not be sparse anymore. So actually, we don't know any better than just using our algorithm or the naive brute force solution that runs in mn time. Also, it's pretty interesting to actually think about how this, what is the relation of this problem with other problems, like, let's say, intermediate complexity problems, or these problems that can be computed in n omega time. Yeah, basically, these are the two most interesting questions, I think. Yeah, and I think that's it. That's what I had to say, and I welcome your questions.
I have a question about, I mean, since you cooperated with Pino, I'm obliged to ask, what happens in the case of, say, a dynamic directed acyclic graph?
Okay, so that should probably also be on this slide, right? Of open problems.
You seem to like this question very much.
No.
I don't think that we even talked with Pino about this, right?
We should.
We should, right? I remember.
I'm not sure if I feel brave enough to consider a fully dynamic case, maybe incremental or decremental as a starting point.
Yeah.
So let me reformulate the question. So since you have this AB decomposition, right?
Yeah.
Into chains and antichains, how about maintaining such a decomposition in a dynamic setting?
I thought about this for a little, but it appears hard for me. I don't know. This is like, yeah, but it's a good point and probably a very nice direction of the further research. Yeah, I agree. The other thing is like about this decomposition is that we don't know how to use sparsity there as well. So we like our techniques gives us something like O of n times square root of n if you want to compute this decomposition for a sparse graph. And we don't know if this can be done like any better.
There's like, we conjecture you can compute this decomposition in time just linear in number of edges. It doesn't need to be n squared, it can be just O of n. Okay, I'm going to stop the recording. Maybe that will encourage people to ask the questions.